Guys, welcome to the channel. Today we are going to design a synchronizer. A synchronizer is a sequential circuit which is used to synchronize the deep flip-flop to another deep flip-flop. So basically, the issue that we are facing is that if we are not using synchronizer, it produces an output queue within unbounded amount of time, so that the output queue will depend on D whenever if there is a falling edge, if D is 1, then output Q may not be 1 because it will be 1 only at the rising edge. But during this amount of time, say like if D doesn't remain 1, then output Q will not be 1 within that time. So what is synchronizer shown in this figure is that it is a device that receives asynchronous input D, also a clock, and produces output Q within bounded amount of time. So the output has a very logic level which is extremely high probability. So this is the reason we are using a synchronizer here. The only issue is that this synchronizer will fail only if the output of the synchronizer becomes metastable. That is, D is between high and low. But that case will is rarely occurring, and this synchronizer will give correct output with high probability. This is the circuit diagram of a synchronizer. We'll have an enable pin, a reset pin, a clock as usual, and also a 4-bit D input bus and a 4-bit output bus. Uh, the wire that will be connecting the first flip-flop and the second flip-flop shall be named as uh, Q naught. But since we are using but since like we are using an always statement, it will be declared as a edge and not wire because uh, expression inside and all this statement need to be read as per the rules of Verilog. So we'll proceed with designing the circuit. Okay, so it will have input enable, input reset, all are 1-bit input clock, and there will be 4-bit input D, a 4-bit output which is declared as reg because it will be assigned inside an always statement, and the output shall be named Q. Okay, let us declare the intermediate wire Q naught, which should also be a 4-bit. Let us name it Q naught as per the design, and after that we have to write our sequential logic using always statement. Always at the rate sensitively cos h clock, cos h reset, keyland. If enable is on, if reset is on, output should be or Q should be using non-blocking assignment 4-bit 0. Else, if enable is on, okay, what should be Q? Here we'll try to begin and end statement because we'll have two statements at least. First, what we'll do is assign D. Now enable is on, right? So Q naught should be non-blocking assigned to D, and Q should be non-blocking assigned to Q naught. Okay. So here our synchronizer logic is completed. We check for any syntax error if there is any present. Okay, no syntax error are present, so we can proceed with synthesizing RTL schematic. I double click this. Okay, now our synchronization circuit is done. It has actually a 4-bit D input, 1-bit clock, enable and reset, and a 4-bit output bus Q. And double click is to see what circuits are used. Okay, so as shown, actually, flip flops are used here. Both are D flip flop. Okay, and these are like connected to the circuit enable. Like, using our enable logic, and also like the reset is connected appropriately to this flip flop. And both resets of this flip flop are interconnected. Okay. Also, like both clocks are also interconnected to this flip flop. And as you can see, the output Q naught. This is Q naught. You can like see through this. Q naught, which is a 4-bit burst, it goes to the input of another D flip flop and produces output Q, which is this. Okay, I hope this is clear and let me know if you have any doubts in the comment section. While writing the test bench for the synchronizer, it will be like similar to the one shown in the previous lecture. So the test bench will remain almost the same. Okay, thank you.